All right, hello class. Um, Thank you for watching. Uh, you might notice that I'm about 2 feet to the right of where I normally sit. I normally sit on the floor in front of the coffee table, or in front of the couch with the coffee table in front of me. But I'm sitting a little bit to the right today because Hazel had a big uh-oh on the carpet yesterday, and um, uh, she really knows how to do a big uh-oh. And luckily it wasn't on the couch. It was on the rug that is underneath the couch. That rug is going to need some thorough cleaning. That's actually what I'm going to do after I'm done teaching this lesson today. Um, so I'm going to get through this as quick as I can because it stinks. Hello, Sebastian. Hello, Elena. Hello, Ella. Um, I actually I went for a run earlier today, and I ran past Lisa. So if you know Lisa, she kind of lives by Foothill Country Day School, I think. That's where I saw her, at least. Okay, so let's get to it. So we're doing some simple harmonic motion today. Starting off with this problem. It says a cart of mass m is attached to an ideal spring that can stretch and compress equally well. The natural length of the spring without the cart is at point E. The cart and the spring rest on a smooth angled track. The cart is pulled to position A and released. The cart then moves towards position E, where it reverses directions and returns again to position A. All right. Sketch energy bar charts for the cart spring earth system at the 5 labeled points. So at point A, we have the kinetic energy and the gravitational potential energy are zero. Because why is the kinetic energy zero? It's because it's an extreme point. It's as far as it goes. So it's at rest momentarily at point A. And then if we look at the gravitational potential energy, we're just defining y equals 0 to be right there. Okay? Now we can see if I look at point E, we have 16 units of gravitational potential energy, and the total mechanical energy is conserved. So that means that the elastic potential energy right here had better be 16 units. Okay? So this is going to be 16. Okay? At point B, we have at point B, we've got less elastic potential energy because the spring is less stretched. Okay. We're also going to have more kinetic energy. But if we look at point B is a quarter of the way to point E. So that means that we're going to have a quarter of the gravitational potential energy at point B. So the gravitational potential energy at point B is going to be 4. So maybe that much. Okay. And then the kinetic energy, because our total energy is 16, the rest has to be kinetic energy. So that would be 3. Okay. At point C, we've doubled in elevation from point B, so we're going to have 8 gravitational potential energy. as far as elastic potential energy, well, let me do point D first, because that'll make it easier. Point D is 3/4 of the way there to the highest point. So it's going to have 3/4 of the gravitational potential energy, which would be 12. And that gives us a kinetic energy of the remainder. So that would again be 3. Then if we look at going from D to C, point C is stretching the spring, twice as much. And you might remember the formula for elastic potential energy is 1/2 kx squared. So if we double x, we're going to square that double and get 4 times the amount of elastic potential energy. So 4 times 1 is just going to be 4. So the amount of elastic potential energy is 4. And then the remainder of the energy is going to be kinetic. So that would also be 4 of kinetic energy. Okay? So there you have it. So I just explained it in words, so I'm not going to type it all out. Do the energy bar charts depend on whether the cart is moving left or right? I would say no. Because, see, now she's panting. I'm worried she's going to have another, I'm going to put her on the ground. Hazel, you go to the ground. You go to the ground, Hazel. Go. Be free. So I would say no, because basically because the only part of the energy that depends on velocity or direction of motion, which is the velocity, is the kinetic energy. And the kinetic energy has v squared in it, which means a negative is squared away. Okay? As the cart moves from A to E, the total energy of the system should be the same at each labeled point. Explain why this is the case. So why, basically, the total energy can only be conserved, or can only change if something outside the system is transferring energy in or out. There is nothing outside the system interacting with it. Okay? As the cart moves from A to E, the gravitational potential energy should increase by the same amount between each labeled points. Explain why this is the case. I would say the formula for gravitational potential energy is mgy, which is a linear dependence on y. Okay, so it has a slope, a constant slope. So that means that, so we get the same change in potential energy for equal changes in y. So what that means, because the change in elevation between A and B is the same as the change in elevation between B and C is the same as the change in elevation between C and D, we're going to have this equal amounts of change each time. As the cart moves from E to A, the spring potential energy should increase quadratically between each label points. Explain why this is the case. Well, I would simply say that the formula for elastic potential energy is 1/2 kx squared. So I don't know if they're trying to I'm not sure if they're trying to get us to explain why is the elastic potential energy 1/2 kx squared. I don't think that's what they're asking, so I'll just state the formula. Okay? Let me see if I have any questions. Yeah, when I saw Lisa, she looked like stunned. It was really funny. I don't think she recognized me immediately. All right, so the next workbook pages I'm going to do are 172 and 173. So that's this one. Angela and Blake are given a spring and asked to determine its force or spring constant. Both students are given a stand on which the spring may be attached. Different known masses that can be attached to the spring and an electronic balance. Angela, in addition to the equipment above, is given a meter stick that has no access to a stopwatch. Explain how she can make a measurement and how those measurements can be used to calculate the spring constant. So basically, what you would want to measure, I'm just going to write it all in one big paragraph. So what I would say is hang the masses, the different masses, record the amount each mass stretches the spring in equilibrium. That's an important point because in equilibrium means when the mass is at rest. Okay. Obviously, if the mass is not at rest, it can be stretching the spring by a different amount. According to net force equals ma, if it's in equilibrium, the acceleration is 0. Okay. So that means that net force equals 0. But the net force there are two forces acting on it. There is the upwards elastic force, and then there is the downwards weight force. So kx minus mg equals 0. And then that says that k equals mg over x. All right, so we can solve for k that way. In addition to the equipment above, Blake is given a stopwatch, but no access to a meter stick or any other way to measure distance. Explain how he can make the measurements. Okay, so this method is basically using equilibrium. Blake's method is going to use basically disequilibrium, simple harmonic motion. So Blake should attach masses to the spring and set them in motion. Record the period of the simple harmonic motion. Then use period equals 2 pi square root of m over k to solve for k. Pretty straightforward. All right. Now suppose that both students and the classroom are transported to another planet where the acceleration due to gravity is greater than Earth's. For each student, list any measurements above that would have different values on the new planet. So notice how if you go to a new planet, it's new gravity. So for Angela, you see how the K value depends on gravity. So basically, if gravity is stronger, the spring is going to stretch more. Okay. So what I would say is for Angela, X will be different. Okay. Because gravity affects the weight force. So basically, the formula depends on G. The formula for K depends on G. So gravity is going to mess around with that equation. For the other equation, gravity is nowhere in this equation. So the simple harmonic motion is going to be, the period of the simple harmonic motion is going to be exactly the same, even if it's on an alien planet. So I would say for Blake, the experiment proceeds as usual. Which student will obtain a different value for the spring constant? In a clear, okay, so both students should get the same answer. Okay? While the alien planet has a different G, the gravity will stretch the spring a different amount. So K equals mg over x will be unaffected. Okay? And so my mom just texted me and she said I should close the curtains behind me. So let me listen to my mommy. Is that better? You can see me now. I guess from your guys' perspective, you want to look at the physics, but from my mom's perspective, she wants to look at me. Okay, so yeah, it should be the same answer no matter what. The final question, the final pages I'm going to do for today is pages 181 and 182. Okay, so here we go. Carlos, looks like this is going to be a linearizing a graph problem. Carlos and Dominique hang a spring with an unknown spring constant from a ceiling. The students connect objects with different amounts of mass, m, to the spring and measure the oscillation period t of the object. Their data is shown on the right. Note that the square of each period is also calculated. The students did not take care to ensure that the object oscillated with the same amplitude on each trial. Their teacher informs them that this oversight will not invalidate their experimental results. Briefly explain why this is the case. So I would say period equals 2 pi square root of m over k. Does not contain the amplitude. So the period doesn't depend on the amplitude, as long as the amplitude is not too large, because if the amplitude gets really, really large, then you're going to basically permanently damage the spring. On the grid, plot a graph of t squared versus m. Draw the best fit line. So 1.15, 0.61. I have to get my scales here. So it looks like the mass goes up to 6. So this will be 6 right here. This will be 3. So this is the mass in kilograms. Okay, and then period squared goes from 0 to roughly 5. So here is 5. Here's 5. Here's 1. Here's 0. And this is period squared, which is measured in seconds squared. Oops, you get it. So my first mass is 1.15 and 0.61. So that is roughly, I don't know, right there. Okay. The next one is 2.32 at 1.46. There. The next one is 3.5, 2.6. 3.5, 2.6. The next one is 4.75, 3.5. 75, 3.5. And then the final one is 5.8, 5.9, and 4.2. So that would be roughly right there. So we can see we've got a nice best fit line that kind of, oops. Undo, what did I just do? Got a nice best fit line that kind of looks like this. Okay? An unknown object hung on the spring oscillates with a period of 1.47 seconds. Using your best fit line, calculate the mass of this object. So let me make this a little bit more perfect. So notice how we have period squared. So on the vertical axis. So what I want to do is I want to calculate 1.47 squared equals 2.16. So what I do is I go to 2.16, which is roughly right here, and I go across the graph, bing, and I see that on my line of best fit, that corresponds to a mass of roughly 3. Okay? So on the line of best fit, when period squared equals 2.16, m equals 3 kilograms. So it's a 3 kilogram mass. Using your best fit line, calculate the spring constant of the spring. All right. So if I take the equation period equals 2 pi m over k square root, what if I square that equation? Okay, I get period squared equals 2 oh gosh, you guys were supposed to do this question. I guess you have one less question to do today because I did the wrong one. Whoopsies, sorry about that. So I get 4 pi squared times m over k. So what I can see, if I write this a little bit differently, I can see that if I graph period squared versus mass, it should look like a line, and the slope of that line is equal to 4 pi squared over k. So now I got to get my slope. So if I look at what is the slope, it looks like the slope is roughly, I've got a rise of about 4.3 and a run of 6. Okay? So my slope is like 4.3 over 6. And I set that equal to 4 pi squared over k. Then I can solve for k. 4 times pi squared times 6 over 4.3. That gives k equals 55 newtons per meter. Suppose Carlos and Dominique also made a graph of period squared versus mass. However, the graph they made has a best fit line with a slightly steeper slope than the line you drew in part B. How would this affect their experimental value for the spring constant? So we found that slope equals 4 pi squared over k. So if the k value goes down, the slope goes up. So that explains what's happening. It's just has a smaller stiffness. How would this affect their value for the mass with a period of 1.47 seconds compared to yours? So if they had a steeper line, let me draw a steeper line here. Okay. And they square the period. When they trace their line, okay. So I'm going to say, oops. I'm going to say smaller mass. All right, so those are my questions for today. I'm going to change the daily item to the one that I was going to do. I was going to do pages 185 and 186. So I'll have you guys do pages 185 and 186 instead, and because I did the problems that I assigned to you by accident. All right. So I hope you guys have a great afternoon, and I'm going to clean this rug. See you tomorrow.